Hello, everyone. This is the video that I promised you where I'm going to prove that the rational numbers are dense in the real numbers. And what that means is that if you pick any two real numbers, no matter how close together they are, there's always a rational number in between them. So a fraction of the form m over n, where m and n are integers. And this is surprising, I want to remind you, because we showed um, that the cardinality of the rational numbers, whoops, the cardinality of the rational numbers is less than the cardinality of the real numbers. So there are many, many, many fewer rational numbers than reals, yet somehow they're sprinkled, these rational numbers are sprinkled around among the real numbers so densely that whenever it doesn't matter how close my two real numbers are, I can find a rational number in between them. Okay. So let me tell you the two main ingredients that we'll need to prove this. So the first ingredient is something that we've used a long time ago, and this is the well ordering. So well ordering. And this is that, remember this says that if X is a non-empty subset of the natural numbers, it has a smallest element. Okay. And remember, this isn't true if for the rationals or the reals, because I can have like these open intervals, open on the left, and then there's no smallest element. It's not true for the integers because I can have sets that go to sort of minus infinity in the integers. So this is really special for the natural numbers. And then the other thing that we're going to need to use is the theorem that I told you, or the property that I told you about the other day. This is the Archimedean property of the real numbers. So I'm going to write Archimedean property. And this says that if I have two real numbers that are both positive, then there exists some natural number n such that a is less than n times b. Okay, so the idea is even if I made b really, really, really small, like 0.00001 or something like that, if I took a big enough little n, if I took a big enough natural number, I could make n times b bigger than any fixed number a. All right, so I'm going to use both of those properties to prove the denseness of the rationals. And before I actually do the formal proof, I want to give you a sketch of how it goes. So the idea is this, suppose here's my real number line, and suppose I have my two numbers, real numbers A and B, and I want to find a rational number in between them. Let's look at the distance between them, B minus A. So that's this distance. And the idea is that if b minus a is bigger than 1, then there has to be an integer in between them. Okay, that is going to imply that there's an integer. There exists an integer m, an m in between them. Okay, and so if b minus a is not bigger than 1, I'm going to use the Archimedean principle to find a natural number. I'm going to blow up, sort of inflate the interval from a to b, and I'm going to look at, I'm going to see if I can make n times b minus a greater than 1. So then I'm going to look at this interval from na to nb, and if that n times b minus a is bigger than 1, there's going to be some integer in this interval. And then to find my rational number, I'm just going to divide by n. And so then a is less than m over n is less than b. Okay, so that's my idea. So let me put that into a formal proof now. Okay. So the way the proof goes, I'm going to start by using the Archimedean principle. So by the Archimedean property, there exists a natural number n such that n times a minus b is, n times b minus a is greater than 1. Okay. Oh, and you know what? I think I want to say that, I'm going to prove this in this special case where a is positive. So let's say that here. So assume a is greater than 0. That it's not that big a deal, and yeah, it's not that big an assumption. It just makes this one step in the proof where I use the well-ordering principle a little easier. So let's just assume that a is positive, and b is bigger than a. And by the Archimedean property now, I can blow up the interval from b minus a until that interval has length that's bigger than 1. And now I'm going to define the following set. I'm going to say let X be the set of all natural numbers R such that R is bigger than N times A. All right. And in fact, here I'm sneakily using the Archimedean property again because I'm saying, well, NA is positive, and you know what else is positive? The number 1. So R times 1 is going to be bigger than NA for some natural number R. Okay, so I know this set is non-empty. So I'm going to say by and I'm going to use AP for Archimedean property. Again, X is non-empty. And I've defined it to be a set of natural numbers. So now I can use well ordering. So by the well ordering principle, X has a smallest element, and let's call that element M. Okay, that's the integer that's going to be between NA and NB. All right. So there are two inequalities I need to show. I need to show that M is bigger than NA and N is less than NB. I'm going to do NA first because it's easier. Okay. So by definition, uh, by definition of the set X, the only way a number, a natural number can get in the set X is if it's bigger than NA. So little m is in that set. So by the definition of X, little m is bigger than NA. And this tells me also if I divide through by m, or sub by n, that mn is bigger than A. So now I have a rational number that's bigger than A, and now I just have to, I'll be done if I can just show that rational number is less than B. All right, so here we're going to do the other inequality now. So first I'm going to say, well, note that M minus 1 is strictly less than M. Okay, M minus 1 is less than M, and M, remember, by definition, it's the smallest element in X. So I'll say since M is the smallest element of X, m minus 1 cannot be in X. Okay? Now, if it's not in X, what that means is that it can't satisfy this property, the property that makes natural numbers get in X. So what that tells me then is that m minus 1 has to be less than n times a, which tells me that m is less than 1 plus na. All right, so what do I do now? Well, remember, I defined little n by saying that it satisfies this property, that n times b minus a is greater than 1. So let's use that. So I'm going to say recall that n times b minus a is greater than 1. And so this inequality is going to let me relate n, a, and b. Okay, so this says that nb minus na is greater than 1, which tells me that nb is greater than 1 plus na. Hooray! So now I'm going to put this together with this, and that tells me that therefore, m is less than 1 plus na, and that's less than nb. So now if I look at the beginning and the end of that inequality, I see that m is less than nb, which implies that m over n is less than b. And now, hence, I know that a is less than m over n, and that's less than b. And so I've got my rational number in between my two real numbers. And this was a kind of cool proof because note, it was essentially constructive, right? I told you how to get it. So if you have two real numbers, you can blow them up, blow up the interval, find an integer in between them, and then just divide by the factor by which you blew up the interval. And you'll have your rational number between any two reals, which is very surprising because remember, there is so many fewer rational numbers than real numbers. Okay. All done.